Okay, can you ask them if they can hear online, Josh?
And everybody,
Oh, okay. Let's okay, can you say something?
Yeah.
Okay.
Do you hear me? Okay. Okay, first of all, thanks for the invitation, and I also want to thank Andrew Roberts for the talk before mine, because he got the most difficult job to condense the universe of FORC into 45 minutes, something I would not be able to do, for instance. So here I will just take the playful part in a certain sense and play a little bit the devil's advocate and show you some paradoxical aspect of FORC processing in a provocative way, hoping that I can stimulate some thinking about how do you organize the measurements. Sometimes you do your FORC diagrams and then you process the data and you realize after that something went wrong with the measurements, but you don't have access to the machine anymore, for instance. So
Clicking on the mouse.
okay, yes. So well, today the arrow not work? Okay, so this is the outlook of my talk. So there is a brief introduction, then I will speak about preparing your measurements, and then I will speak about processing, and finally post-processing and representation. All the examples shown here have been performed with FORC. That's my processing software, so you can scan the code and access it. There is a very complete manual, so if you don't understand details of the talk, don't worry. They are explained, technical details in the manual, and there are also examples. So, okay. So let's start with the challenges. So typically, what is the scope of FORC measurements is to scan the small area that is inside enclosed by the major hysteresis loop. Okay, so you just cross this area with many curves, and with this you have access to changes in the magnetic states of the particles inside the hysteresis loop. And you already see what's the problem. Many hysteresis loops are quite closed by nature, and you need to resolve actually 1% of the opening in zero field, which is the saturation remanence. And so you get to have a lot of curves condensed in a small space. And that means that you have to fight against noise and have a good signal to noise ratio. On the top of that, the remanence itself is small compared to the fields, to the magnetization that you are measuring in the fields. And on the top of that, many samples contain a lot of paramagnetic materials, which compress or squeeze the ferromagnetic contribution down farther. So this is the first challenge. The only way to solve it is have machines that are more sensitive, and Lakeshore, for instance, is behind it. The second point are processing challenges. So when you process your data, many times, I mean, we think that dealing with dirty material means that you don't have particular functions with particular mathematical properties, but in fact they are quite common in natural samples. For instance, this curve can have a discontinuous first derivative. And now when you do your processing, you assume that the curves are continuous, the derivatives are continuous, you fit them with polynomials, and you get processing problems. For instance, this is something that usually happens near the origin. Finally, there are challenges in how to represent the FORC function. And these challenges actually have prevented until now to look at FORC diagrams in a more quantitative way, in my opinion. And the reason is that when you look at the FORC diagram, you're not looking at the magnetization, you're not looking how much, for instance, this feature here, the central reach, is contributing to the total magnetization. Yet, this is a very important thing. How much does this reach contribute to the total magnetization with respect to other very low amplitude contributions, which tendentially are disregarded? Okay, So this is a big challenge as well. And so I will just keep the sample preparation short and defer to a paper by Andrew Roberts on that. He shows how samples should be prepared. Here, I just say something: if you deal with powders, be careful to press them firmly, because the vibrations in a vibrating sample magnetometer will tend to lose those powders. Don't fill the caps too much, because the aspect ratio, if you make the aspect ratio too long, you just don't get the correct measurements at the end, if you must normalize them due to the response of the instrument. If you use fragments, be careful that the fragments are not too wide. They just have to occupy the central region between the poles, ideally half of the distance of the poles, not more than that. And the region is coming in the next slide. So this shows, for instance, a sample in place between the pickup coils, and here you show the two magnets. The response function of VSM is a parabola. So that means that there is a region, a central region, where the response of the instrument is relatively insensitive to the position of the sample. And the position of the sample is determined by centering. Now, even if you don't care about absolute values, you don't want to calibrate your measurement, it's important to have them exactly sitting in the center, because if they are slightly off the center, any variation in the lateral position of the sample, for instance, due to some turbulence in the air, will produce noise. So you just don't center carefully, get more noise. And do not use too excessively large samples. If the sample comes close to the poles, actually you go outside of this optimal region for the response function of the instrument. And again, the response will be very sensitive to the position of the sample, and you will get noise. So these are rules that needs to be considered to optimize the signal to noise ratio. Then another problem is when you have to plan your measurements is what range are you going to measure with FORC diagrams? And here you see some extreme examples of very unusual FORC spaces covered by measurements. This is a multi-domain sample. You saw example by Andy Roberts. This is one where hematite is inside. So you have to decide what are you going to, where do you want to focus? And in many cases, unfortunately, important regions of the FORC diagrams are carried out, and you cannot do anything with post-processing then and resume this information. So be careful about that. So here, what is behind the FORC range selection is what I call the saturation field. The saturation field is the field where the major hysteresis loop closes. And this is actually the most important point to consider to plan your FORC measurement. So first of all, run a hysteresis loop and look where the hysteresis loop gets closed. Of course, if you have mixtures between low and high cursivity minerals, it never gets closed really, but then you have to select and say stop at a certain point and say, okay, low cursivity mineral contribution will stop in a certain field. And then what is behind, you can really see it by looking at individual example. You saw for before example from single vortex particles. This is an example of a system, a magnetic system composed of interacting single domain particles, which has 3 magnetization states. Okay, and you see the mass that is already producing this. So every transition between states will produce a peak on the FORC diagrams. But the nice thing is that this peak tend, and underline tend, to be inside the limits in the FORC space determined by the saturation field. So this field, the saturation field, you see it here, that's the maximum cursivity, and you see it also in the vertical axis. Now, if you speak with a physicist, he would tell you that the individual FORC curve can also exceed the saturation field. But let's say, for the sake of practice, with the help of statistics, this excess is insignificant in the samples we are looking at. So you can consider really that all transitions you are interested in are within this region. And that's practically the region you should try to cover with your measurements. Here you see the example of ion, which was shown before. So the case of this is a macroscopic measurements, and these are again, micromagnetic simulation done on individual particles, and you see that individual peaks tend to be contained into this triangular region. So now coming really to the FORC range, there is another point to consider. This is our triangular region, which we seek to cover with measurements. And let's say that you decide that the region of interest is this squared region here, which is characterized by the parameters, the FORC protocol parameters, 0, HC max, and then the minimum and the maximum on the vertical axis. And you see here that to measure this lower right corner of the FORC diagram, which does not contain any.
Get to the pointer.
Okay.
We can online, but we can't hear.
Okay. The lower left part of the FORC diagram is not containing useful information, but it must be covered by measurements when you use conventional processing. So you will be you need to measure a lot of curves that do not have any function. So if you use processing software that do not pretend to have a rectangular area being covered by measurements like VariFORC, you can spare these measurements, keeping in mind that the region of interest is this triangular region here. Is it possible to show the somehow
The laser pointer.
I think so. Josh, do you know which thing it is on Zoom? I've not put it up. Is it this thing?
Yeah, try that. Or the spotlight tool. Yes.
yeah, okay, perfect.
Maybe
No,
No, we're not seeing it on
we're
there.
seeing it online, but not on the screen there.
Okay.
I'm sorry. I try to describe it by giving the location and in the slide. Okay. Yes, okay, right, simple hardware things. So and here you see some example actually for different types of FORC diagrams. Some of them you see already in this presentation. For so-called pseudo-single domain samples, that this in the middle, this rule that the domain of the FORC function is inside this triangular region is quite good, respected. On the left hand side, you see single domain particles. In this case, it depends whether the particles are non-interacting, and in this case, the upper region will not be covered by measurements, but as soon as you have some sort of interaction between the particles, you also have contributions above the horizontal axis. So another thing that needs to be considered is resolution. Unfortunately, even if we deal with dirty material, the sample we are measuring have sometimes they have important contributions in the small regions of the FORC diagrams. For instance, the central ridge here. Okay, so this requires high resolution, and also you can have diagonal features. This descending diagonal here is also an important region in the FORC space. It's a region where you have low and high torsivities, or low and high switching processes interacting with each other. And in this example, in the left plot, you see actually a measurement done with the old VSM, the PMC 3900. The step size was 1.4 millitesla, and the smoothing factor was 6. The smoothing factor is used to reduce noise. And the resolution is actually the more or less can be defined as the answer to an infinitely sharp peak. So how this peak will be represented when you process the data, and the full width to half maximum. So the full width to half maximum is equal to the product between your field step, delta B, and the smoothing factor. So you have to keep that in mind. So in this case, the resolution, the full width to half maximum is, on the left example, is 9 millitesla. And if you look on the diagonal, on the descending diagonal, this resolution is exactly the distance between the two diagonal ridges. And in fact, although these ridges can exist, they have a physical origin. In this case, they are a measurement artifacts. But with this planning of the measurements, it's not possible with post-processing to know if this is an artifact or it is a real feature. So this sample was remeasured at higher resolution. The step size is 0.4 millitesla. It was done with the new Lakeshore, which is a little bit more sensitive. So the smoothing factor could be reduced to 3. And now you see the resolution, the full width to half maximum is just in between these two lines. And actually this artifact along the diagonal disappeared. So resolution is important, but is also an enemy of time, because if you double the resolution of your measurements, you will multiply the measurement time by 4. Okay, so this is a big issue actually, which can only be overcome by having faster and more sensitive measurements. And then we hit the wall of what hardware can do. Another problem is drift. And I'm not speaking here about instrumental drift. For instance, the new Lakeshore magnetometers is virtually free of drift, completely free of drift, but I'm speaking about drift of the sample due to temperature changes in the room. And now you might think, oh, I have air conditioning, the temperature of the room is controlled within 1 degree, but 1 degree is sufficient to cause trouble in FORC measurements. And why? Because again, remember my first slide, we are looking at very, very, very tiny variations on the magnetization. And so here you see another representation, which is provided by VariFORC. When you import the FORC data, you always have this FORC with this diagram shown. So in this diagram up here, you see the applied fields on the horizontal axis, and you see on the vertical axis the number of FORCs. So measurements we run horizontally from left to right. To the right of this diagram, you see the calibration measurements. So before each FORC is measured, the calibration is measured at the maximum field, and as a function of FORC number. And you see with the calibration measurements that suddenly air conditioning was turned on down here. Okay, and this caused a temperature change of 2 degrees, and this was sufficient to produce these stripes that you see here. The stripes represent variations in the spontaneous magnetization of the sample, which cannot be corrected because they are faster than the interval between two consecutive calibration measurements. So if measurements, temperature changes, even little temperature changes are too fast, you are not able to correct them. So my suggestion is, if it is possible, turn off air conditioning. In this case, you have the natural daily cycle in your room, temperature cycle, and this is better, can be handled much better. The second aspect of drift is temperature can act on the coercivity of your sample. Actually, the coercivity can be more sensitive to temperature than the spontaneous magnetization. And you see an example here. This is a sample that is very sensitive to, where the coercivity is very sensitive to temperature. And you see that the horizontal stripes are like condensed at places where the hysteresis loop has the maximum slope. Okay, so this has nothing to do with the spontaneous magnetization. It really has to do with lateral changes in the position of the curves, which is due to coercivity. And this cannot be removed because you don't know how coercivity is changing. Okay, so the only thing is try to suppress temperature variations in the room. Then there is something that Andrew Roberts also said already a little bit. There are issues with the reversal field. It's very complicated to move the field from positive saturation to the reversal field. Is my favorite image for that is if you're trying to push a train and make the train stop exactly with a 1 millimeter precision. So the mass of the train is the inductance of the electromagnet. So this is a very challenging thing. And you see here also a very challenging sample. These are the original measurements, a lot of paramagnetic contributions. So all the ferromagnetic stuff is condensed into an invisible region. If you do the paramagnetic correction, it gets better. Then you can also subtract the lower branch of the hysteresis loop, this here, from all measurements and get the differences. The differences really blow up the space that is enclosed by the hysteresis loop. And here you see that each curve begins with a hook. And this, you heard from Robert, can be due to viscosity, but it can also, in this case, it's not due to viscosity. And the reason is that, I mean, this hook is producing a vertical ridge, you see it here on the left, but this ridge exceeds the saturation range of the sample. And viscosity, there is no viscosity when you saturate the sample. So this is actually a typical example of an artifact due to difficulties in controlling the reversal field. FORC offers the possibility to correct this first measurements. The correction has been applied here, and you see that the ridge disappeared completely. Noise is left, but still, yeah, at least you don't get an incorrect interpretation. Then there is also the reversal field is also actually controlling the offset of the central ridge. You see here, these are viscous, non-interacting single domain particles from the Tiva Canyon in a paper by Bernd and others, and you see that it is offset vertically. And this vertical offset is due, in this case, to thermal activations. In the right example, it is quite large. It is something like 3-4 millitesla. It's almost never seen in nature, such a large offset. But in any case, you also get a vertical offset of your entire FORC diagram if the Gauss probe of the instrument is not zeroed. Okay, so with the new VSM, you have a little mu metal box and you can zero the whole probe, and that's the Gauss probe. And this is a very important thing to do, especially when you're looking real example or more realistic example of the vertical offset of the central ridge, like in this example of magnetofossils from the Paleocene Eocene thermal maximum. You see a blown up version of the central ridge, and you see that the position of the vertical position of the central ridge is changing, and this was pointing to a very special type of particle, needle-shaped particles in this case. And this measurement, because overshooting at the reversal field can be a problem, was handled very carefully. So here you see, for instance, that one good thing that you can do with the new Lakeshore magnetometer is that you see this on the left diagram. You can have control of during the measurements, and you can see what happens to the field when you're doing something. So now on this diagram on the left, you see that first of all you saturate your sample, then you go to the calibration field. So calibration above there, you go to the calibration field, and then the field is ramped down. Please notice that the scale is logarithmic, and then there is a last adjustment. So the yellow curve is the set field, and the blue curve is the real field, and you see that there is an overshooting. It's only 0.15 millitesla, so it's really nothing, but for the central ridge offset is already enough to produce an incorrect interpretation. So in this case, you can use a scripting possibility of the new instrument and add some steps. Instead of shooting your field directly from the calibration field to the final reversal field, you just stop a couple of steps before. And this allows the machine to recover in a certain way from this procedure, and you will at the end approach the reversal field without any overshoot. Okay, so if you are planning to look details of the central ridge for some reasons, use this procedure. So then we are coming to processing. So as you probably know, what is behind processing, what is behind calculating, the FORC function is taking the mixed second derivative, and this is done by fitting regions of the FORC space with a second order polynomial. So on the left diagram, there's this blue square. This is the traditional processing as it was introduced by Pipe. The size these rectangles, these squares are oriented in measurement space, so the blue coordinates, and the size is given by the smoothing factor. Later on, a more advanced processing was introduced, where you can basically choose an arbitrary point in your FORC space and have a weight function that consider a certain region. So the gray level represents actually the weight that you're giving to the function, and this trick performs much better, for instance, at the left edge of the FORC diagram. This is called the less fitting algorithm. With FORC, the approach is a little bit different. This you see on the right diagram. You choose point where you want to calculate your function and the rectangular region in FORC coordinates. So there is not a square, it's a rectangle, because you can choose to have different smoothing factor in different directions. The reason why will become evident in a moment. But it's also useful to work in measurement coordinates. So again, go to the blue coordinates. And sometimes it is necessary to have a large resolution at certain value of the measurement field. And so you will have a rectangle that intersects with the red rectangle to limit your smoothing factor where it's needed. So I know that looks very complicated, because actually now the smoothing factor is defined along 4 different directions, the 2 coordinates of the FORC diagrams and the 2 measurement coordinates. But this is needed. So, and then, but let's go back again to the simple case of isotropic smoothing. So you have a single smoothing factor, and you just apply this to your entire FORC diagram. So you will see if the smoothing factor is too small, you get almost only noise. And then you increase your smoothing factor, and you look what happens with the residuals. So the difference between measurements and the model, and you see that there is an initial increase, and then you eventually reach a plateau, where the results do not depend so much on the smoothing factor. And this plateau represents the ideal smoothing factor. You have removed noise, but you are not touching the intrinsic FORC function. If you increase the smoothing factor too much, so you go to the right in this diagram, you start to over-smooth. That means that you start to remove the real character of the FORC function. So, and this is a simple way to find the ideal smoothing factor. However, there are samples where the situation is more complicated, like the example shown below. In this example, you see that the residuals do not have a plateau, so they always increase. And this means that at any smoothing factor, even a smoothing factor, the smallest one of 1, you will alter your FORC function. You will have fitting problems. And the reason for that is that this FORC function contains a one-dimensional feature. So the infamous central ridge. And it's not possible, and this is something that you have to keep in mind, it's not possible to process this ridge character. But there is a workaround that I will speak about later. So one solution, anyways, to this problem is to use different smoothing factor at different places in your diagram. So depending on the feature on which you are focusing, you use a different smoothing factor to obtain a different resolution. And of course, this is complicated, but it is done in a progressive thinking way. So the first step is to reason in FORC coordinates. So BC and BU, or BI, in the case of Andy's talk. And actually, one rule, and this people that work with coercivity distribution know, one rule of coercivity distribution is that if when you move to large fields, higher coercivity, the curves become smoother. There are less details. So your resolution can decrease when you go to larger fields. And this works in both directions. There are exceptions, of course, but this is a good general rule. And this is shown here. So on the left, you see constant smoothing factor here, in this case, smoothing factor of 5 on the top. And on the bottom, you see a plot which shows significance of the calculated FORC function. White, yellow, red means the function is significant. Blue, it means that it's not significant. So you see that there are large regions of the FORC space which are not significant at all. So what you can do is to increase the smoothing factor as you are moving to the right and as you are moving away from the horizontal axis, right? So you stretch basically your smoothing factor in both directions. And the result is that you keep the large resolution that is needed here, for instance, around BU equal to 0, but you increase enormously the significance region of your function. So that's the basic, let's say, that this can be applied always. But then there are critical regions, and these critical regions where you need high resolution can be everywhere in your FORC diagram, and this needs to be taken into consideration. To start with, I first show a region in the FORC diagram. These are the measurements, which is regular. There is nothing strange. You see the curves are smooth, and this represents the ideal case for processing. They can be fitted with a second order polynomial, and these are the residuals on the top there, and the residuals are almost 0 and can be modeled by white noise. So that's the ideal situation. And this will be this point in the FORC diagram. Okay. But then this is a sample that contains the central region. The central region measurement space is the point where the curves, the red curves, join the upper branch of the hysteresis loop. And when this happens, the point where they join is a corner point. It's a point where the first derivative is discontinuous. And so and this creates a fitting problem. A polynomial has continuous first derivatives. And so you get a larger residual. You see that by the red curves. And this will be the central region. Then in this particular case, there is also the region around zero quiet field. Okay. This looks almost normal to the naked eye, but if you zoom in, you will see that actually when crossing 0, these curves change their slope abruptly. And this is again a manifestation of viscosity and something else, which I will speak about on Wednesday. In any case, the first derivative is discontinuous. You have very large residuals, you see here, and so you have problems with the representation. What happens in the FORC diagram? So B equal to 0 is the diagonal here in the FORC diagrams. What happens is you see that the lower plot is representing the error. You see that there is a large error here. But in the FORC function, in this case, fortunately, you almost don't see anything except noise. But this is one example. There are other examples where you create artifacts along this diagram. So one way to get rid of the problem of the discontinuity, and this is shown here, for instance. You see the dashed line is indicating the slope in 0 field of the lower branch of the hysteresis loop, and you see when you go to positive field, the slope increases abruptly. And one way to eliminate, in most cases, this problem is to subtract the lower branch of the hysteresis loop. That means the red curve is to subtract it from all measurements. You will get now a representation where this discontinuity in first derivative has disappeared. There is a rule. You can subtract from your FORC measurement any type of curve, any function, and the FORC will not change because we are actually looking at the second derivative. So this lower branch subtraction, the problem is that the traditional FORC protocol does not really cover the entire lower branch. So there must be some kind of extrapolation to do it. Varifork did it for years in that way. I did it for years in that way. Now Lakeshore has added this lower branch measurements to the protocol. So you can choose it with their software to run a certain number of lower branches. And VariFork recognizes automatically the presence of these lower branches and subtract it. Here you see the benefit on the top right diagram. You see the error that is generated if you don't do this operation. You use the measurements as they are. Very large error along the diagonal. The lower diagram shows the same thing as the error of the fork function when you do this operation, and this is a big difference. So this here shows again the benefits of lower branch subtraction. The left plot shows traditional processing. You will get this strange thing along the diagonal, which you have seen before. You have strange features here. You use lower branch subtracted measurements, and all that goes away. So another artifact that can occur and that can be easily overlooked is when you have rectangular hysteresis loop. Rectangular hysteresis loop are loops that have very large slope around BC, around the cursivity. Typically, in our field, this happens when you have samples containing a lot of magnetofossils or samples of magnetotactic bacteria. So in this case, there is difficulty to fit this large change in the curves with the second order polynomial, and correspondingly, if you use a traditional VariFork method or any other processing method, you see that you will create artifacts along the red dotted line. So these two diagonals, which merge at the central peak of the fork function. In this case, you can tell VariFork to limit the smoothing factor along this region. You give a maximum smoothing factor there. And you see that these artifacts disappear. So this is important. There are examples, and whenever you get this type of hysteresis where this is necessary to obtain good results. So now, with that, I probably provoked a little bit of confusion, because you think, how the hell can I know all that? You need to be a super expert to process your data, and it's a real mess. And you get the impression that the results depend basically on the user, and which is partially true. But there are attempts to go away from that, and this is I think a very nice paper by David Haswell, who is working on that. So basically, the idea to got away from subjectivity is that you start with an initial run where you have a constant smoothing factor, like back to the good old days. And then you are basically looking for each point. You are basically looking in the short phase. You're basically looking whether your fit is optimal or not. What is an optimal fit? An optimal fit is the fit with the largest smoothing factor that gives you random residuals. Okay. So if your residuals are not random, your smoothing factor is too large and you are underfitting. So this is exactly sort of the brown typing there. And you see this here on this diagonal, because this is a sample which had 20 units per stereotypes in Geosphere. And this region is underfitted. That's not good. Overfit, these are the black regions, are regions where your smoothing factor is too small, you are fitting noise. Okay, that's also not ideal. And finally, the blue region is the correct one. And now what you can do is, for every of these points in this diagram, you look if you are underfitting or overfitting, and you adapt your smoothing factor accordingly. The problem is that you can imagine how many points are there, and you have to do this along the 4 coordinates, which I mentioned before. That takes ages, because you need to have, I don't know, more than 10,000 different runs of your fork diagram. But let's say that you have a wonderful machine that can do that. So you do your processing, and then you can represent here the amount of data that are optimally fitted, which are down in this corner, underfitted up there, and overfitted. And choose actually point here, which is the closest one to the that has most optimal data inside. And this will be the optimally processed FORC diagram. In reality, what it was done in this paper was to simplify the problem by using VariFORC approach. The VariFORC approach is controlled by 5 parameters. You have only to change 5 parameters. And so you don't have to run so many simulations. And here is the same example, but now the lower branch has been subtracted. Now, if you recall before, you see here the optimum was away from the ideal case. With the lower branch subtraction, you see that you are coming much closer to the optimal case. Okay, this shows again the benefits of lower branch subtraction. This is something in progress, I think, and maybe in the future you press a button and you will get the optimal processing. And finally, I would like to to go progressively into the conclusions with problems of representing your data. Basically, one of the problems is rendering. And I know there is a bad joke, especially among parametrists, that this issue is related to choosing nice color scales. But I hope now today to convince you that this is not the case. So this is, the left plot is just typical color scale you can find in MATLAB or Mathematica. And you see here that in this specific case, you see only one feature, the central ridge. This is a lake sediment with marine deposits and nothing else. So the problem is here, 2 problems. First of all, that there is confusion between positive and negative contribution. There are negative contributions here, you don't see them, and they are important. And the second issue is that low amplitudes are completely missing. So you're looking basically 2% of the FORC function. Things gets a little bit better when you choose a nice color scale. What is a nice color scale? It's one that ties 0 amplitude, white, let's say, and then you can distinguish between negative contributions, which are bluish, and positive contributions, which have warm color. Here also contours are drawn. These contours are drawn in equispace, which is something that is commonly done. Every 10% there is a contour, but the situation didn't improve so much. You get a hint that there is something more than only the central ridge, but you don't really see anything much more than in the first case. So again, we have the problem that low amplitude are not represented correctly. However, the color scale is a nonlinear one, so you can crank up, let's say, the color contrast at low amplitude and make things become clear. But this is again a very subjective thing. So you can make your FORC diagram appear completely different. This is the same color scale. You see the difference. The only way, in my opinion, to go to an objective representation of the FORC function is to use quantile contours. These are the particular type of contours which are represented here. Let's take the contour which is labeled by 10. This is the 10 quantile contour. Is defined so that FORC amplitudes that are smaller than this contour here, that the contour level, contributes to 10% of the total magnetization. That means all what is outside of this contour contributes to 10% of the magnetization of the sample. Conversely, we can say that what is inside this contour is representing 90% of the magnetization. And in this way, you get an immediate impression of how much does a certain feature in your FORC diagram contribute to the magnetization. And if you start counting contours, 10, 20, 30, 40, 50, 10, 20, 30, 40, 50, you see that the 50 first contour line is the one that is enclosing the central ridge. So like this, you can already say that the central ridge, so this feature that is the only one appearing in the other representation, is contributing to 50% of the magnetization. So the remaining part is there, it is important, is fighting with us, but we don't see it if we don't do the correct representation. So I stress this. There is a lot of papers. We are speaking here about lake sediments or marine sediments where you have this central ridge feature, and there is almost never a quantification. So how much of these particles that produce the central ridge are inside with respect, for instance, to lithogenic particles. And using this kind of plot can help. So again, quantification, let's come back to the famous central ridge or other features which are unidimensional, so they have only one dimension. In this case, as I mentioned before, it's never possible to have a smoothing factor that works correctly. You will always have the results that depend on the smoothing factor. And this is shown here. This is an early paper where the central ridge was recognized. So old color scale. You can see that the left plot, which has a lower resolution, has a maximum amplitude of 4. And the bottom right plot, which has the highest resolution, has an amplitude of 8. So does this mean that there is 8 or there is 4 of these particles inside your sample? You cannot decide it, right? So in order to process the central ridge, you need to take it away from the remaining contributions and process it separately. And this is done by just looking at vertical profiles. Okay, you take vertical profiles and you're looking at how the shape of these profiles, and you will see that you have the ridge itself. Okay, and you have a background, that's the green line here. And if the resolution is large enough, the background is bilinear, so it's linear on the left and it's linear on the right of your central ridge, and therefore you can subtract it easily. So you get just the central ridge itself without any other contribution, and then you can stack these profiles again together, and you get a representation of the isolated central ridge. And if you integrate this ridge along the vertical axis, you get the central ridge coercivity distribution. And now here is the magic. The coercivity distribution is independent of the smoothing factor. Okay, so it's really an objective way to know how much of these particles are inside your sample. So you don't have to care anymore about processing. And so you are suddenly able to compare different publications where measurements have been performed and processed in different ways. And finally, I would like to conclude stressing another thing that, in my opinion, is not considered enough. And this, okay, FORC is not magic. It will not solve all of your problems. And as the discussion at the end of Andy's talk is showing, there is discussion about interpretation. And here I would add some confusion by showing you these 3 diagrams. So this have the classical single vortex feature, but you see that on the left we have a double chain of magnetosomes. In the middle we have a cluster of single domain particles. On the right we have single vortex particles. So the type of FORC function is the same. But this is as with any other magnetic measurements, we are looking magnetic states, and you can create magnetic states in very different ways, the same magnetic states. But anyways, coming back to what I wanted to say is that in order to quantify FORC diagrams, you can extract information, for instance, in terms of coercivity distribution or magnetizations. And there are actually 3 types of coercivity distribution that count for free inside the FORC protocol. And this is the DCD, the derivative of the DCD magnetization class, so what you run to obtain PCR, one of the data parameters. You have the derivative of the irreversible component of hysteresis. That's a hysteresis coercivity distribution, and you have the central ridge coercivity distribution, which is what I was mentioning before. And now you see here, and the integral of this coercivity distribution gives you magnetization. That means single numbers, which you can compare among samples, for instance. This is very important. And also you see that these coercivity distributions are very different in the 3 cases. And this is one key where you can get a better insight into your sample. I have no time to discuss what is behind that, but it's possible to generate this. FORC does it automatically. You don't have to do anything. Once the FORC diagram is processed, you get this coercivity distribution. And the day plot parameters, very importantly, is just something that is contained in the FORC diagram as well. And this can be also used in a reverse fashion. I don't want to take the subject that Johan is going to tell us in the afternoon, but I think it has consequences with FORC PCA. So the principal component analysis that you do on many FORC measurements of many samples. So each sample here is here in the parameter space, one of these white points. And you have these three end members in this example. So what is important for finding the end members is that you have sample close to the end member. Samples which have average properties, so that they are lying in the middle of your parameter space, are not useful at all. So because FORC measurements are very consuming, and because we cannot take shortcuts and eliminate the resolution or make the FORC space smaller, otherwise we lose details. And because certain parameters like day plot parameter are inside FORC measurements, you can use simpler measurements, first of all, run with simpler measurement to pre-select your sample. And this will save some time. And finally, one thing, there are other types of magnetization which are not captured by FORC diagrams. For instance, ARM, anisotropy remanent magnetization, as the name says, unhysteretic, no hysteresis. So unfortunately, somehow ARM has kind of fallen to these days, not used too much, but I think it's a very good complement to FORC measurements. And you see here two examples where the component analysis done on ARM curves on the horizontal axis is compared with FORC PCA results on the vertical axis. And there is on the top example, it's a beautiful example where this works one-to-one. Okay, and you arrive to the same conclusion using completely different physics. Okay, so you can be quite sure that the interpretation is correct. But there is another example here, another core of marine sediments where there is a disagreement between the two cases. So I think one should never forget to include also other type of measurements when you're doing FORC diagrams. And with this, I would like to.
Use the microphone. I have, I'm Yoav from the Hebrew University and Tel Aviv University. I have very technical questions. So I read in one of your papers about keeping the temperature constant in the room. So we started turning on the air conditioning in the room when we measured faults, and now you said to turn it off. So I'm confused. What you're saying, and also we heard in the last lecture, the previous lecture, that often you want the measurements to be very long. So sometimes it can be many hours, and overnight and day, the temperature in the room can change like 5, 6, 10 degrees, depends. So the question is if you recommend. The problem is with the air conditioning going on and off with and then the quick changes that the air conditioning can make, that's the problem. And if you have large changes but over many hours, that's not problematic.
Yes. Yes, and this is because the FORC function works as a high-pass filter. So basically, you select quick changes or quick or rapid magnetization changes. So if you have your temperature changing slowly, and so let's say between the beginning of your measurements and the end, there is a continuous drift. You're just changing a little bit, for instance, the graphicity of the sample. But take a high pass of these measurements, and this kind of regular slow change will not appear in the FORC function. Instead, if you change the graphicity of the sample, let's say within a packet of 5 curves, 5 curves is something that is captured by a smoothing factor of 5. So over 5 curves, you have a change of 1 degree Celsius. This is going to be captured incorrectly by the FORC function, and it creates your diagonal story.
More technical question. You can go on.
Okay.
So another question is regarding the size of the sample and the way it's in fact you said you don't want it to be too long, you want it like, let's say like a ball, more round. and then you can really center it in the middle.
Yes.
And on the other hand, especially with very weak magnetization, we want as much material as possible. So we started putting a lot of material on the side, and then we have this all elongated. So I think maybe that's not a good idea according to what you said. And maybe another question regarding crushing it or using the material as it's, if it's I use pottery, I do antimagnetism and vessels, so pottery or burnt clay materials. So is it better, you think, to crush the burnt material, or to use a big chunk and just somehow make it round so it can fit in the middle of the sample?
So regarding the first question of the aspect ratio, imagine that you have an infinite rod, for instance, a sample holder. So an infinite rod will not produce, if it is made of a homogeneous material, it will not produce anything, any signal in the instrument, zero. So therefore, you should avoid to have an excessive elongation, because the material that is sitting away from the chamber is contributing less, or even with the opposite sign, to the total of your signal. So that's the reason. So you will not, you have more material, but you will not gain anything. And regarding powders or pieces, well, if you have pieces, it's better to have to use these pieces, because the density is larger, so you have more material in less volume, and this is actually the most ideal situation.
Go for it.
So this is my last question. We found that for some reason, our results are much better when we measure at night, when there are not many people, or on the weekend, when there aren't many people in the building. I don't know if it's the electricity, something, the electricity at the building, people slamming doors. I don't know exactly. Have you seen this? Do you have any explanation?
Probably this is a question for the show, but I give you my personal impression. I don't know about the direct electromagnetic interference, because the main supply is not good enough. I mean, we have a filter for these interferences, but we are seeing that during the night and on Sunday, measurements are better. So there are other factors that comes into play, vibrations of the building, for instance, can be a problem. Magnetic field, stray magnetic field. Imagine that the VSM is controlling the field with a resolution that is compatible with the Earth's magnetic field. And now we have stray fields from an elevator, for instance, nearby. So this can affect the field control, in the sense that the field is measured in one pole cap, but the sample is not sitting on that pole cap, it's sitting a little bit away from it. And if you have a gradient, a field gradient, there is a discrepancy between a player field and real field. These are two things that come to my mind. There might be many other that lecture probably knows better than me.
Okay, so a question about the sort of memory of the experiments as you take samples, they take measurements over time. So as you go from the saturation field to the reversal field on each of these measurements, does it matter if you go to a large reversal field and then subsequent measurements always go to smaller fields, or if you were to do that in the opposite direction, or if you were to randomize the reversal fields in order that should the result always be the same in all those cases? And has anyone checked that?
Before each curve, you apply a positive separating field, and this resets your sample. That means that you should start, you restart always in the same step. So theoretically, it doesn't matter the order with which you set the reversal fields. What matters, so you can keep the order that exists, but what matters is that the reversal field is not overshooting. Because otherwise, you have a nominal reversal field which does not correspond to the real one, and this will create a random offset. But overshooting is largely suppressed already in the standard way in the new nature instrument, but you can also add extra steps, as I did, to really suppress even the smallest residual overshooting that you might have.
Just to really clarify then, for the temperature variation, as long as the temperature doesn't vary in between each of those resets, you should be fine.
Yeah.
Okay, great.
So I had a question about your quantile contour levels, which I agree with completely. I think the linear scale isn't going to work, but how do you go from the second derivative to the total contribution to total magnetization? That first question, and then I'll go to another question after that.
So the total magnetization is defined as the integral of the Hart function over the entire space that you have measured. Just this. So you basically numerically you sum all the pixels and multiply by the pixel size, and this gives you the magnetization. That's what they call the Hart magnetization. And then the contour levels are chosen according to this total magnetization. So you're looking basically the contour level with the, and you integrate outside of your contour so that these contours define a certain quantile of the magnetization.
So on that, there's no reversible ridge though. So is the reversible magnetization included in that integral?
Yes, of course, because these are regular quantiles and there are reversible contribution inside as well. And not reversible ridge defined by pi. This was an extra thing that was added. This one not. But the regular reversible processes that you capture with the standard protocol are included. Yes. So the Hart magnetization is not a permanent magnetization, to be precise.
So then I think when you talk about the integral, you actually answered my second question. So when, for example, you see the 0.9 contour, that means 90% of the sample magnetization is outside of that contour, not actually within that contour. Yeah, okay, right.
Andrew? Yeah. Okay.
Thanks. Ramon, congratulations. I mean, I think you're operating at a Pike level carefulness with measurements. I mean, he would put a plastic bag over the air conditioning vent and take them all up. In those days, it was an AGM, probably a set, but I mean, what you're talking about. I mean, we've said in our papers, the more care you make in your measurements will be rewarded in the interpretability of the results. So I think that's obviously true. But the concern is always, do we have to become an expert like you to be able to make good measurements? And that's always the worry, right? And then do we need to know all the processing tricks that you know in order to do that, which is what motivated the Heslop et al. Automated, optimized processing. And I think you probably reviewed that paper and said it's great, but be careful not to be an expert anymore and hand it over to the black box. So anyway, interested in your reflection on the level of expertise needed to make good measurements and good processing.
Oh, did you want to respond then?
It was a question. The level of expertise that is needed, but I think, well, it depends. I think it goes in both directions, in the sense that when we started, I mean, the experts are always exploring the edges of your ideal knowledge space, let's call it like that. You discover a new type of material or a new feature, the experts are crunching it. In my opinion, that's what I'm seeking to, is that at the end, you create some libraries of different types of components or different types of FORC features. And these can help also non-experts. So you can have some types of cookbook recipes. Of course, you can always have a surprise in a sample, something that has never been seen before. And that's impossible for a non-expert interpret. But I think on the other hand, it's now easier probably to process devise FORC measurements for marine sediments in recent years than before, because of a lot of literature that has been produced on this argument. So I think it's always a balance. And concerning the automatization of the processing, as I say, in principle, it is possible to have a universal working algorithm. The question is probably only speed. Okay, you can make it more perfect if your machine is faster. But, and this is my stretch on the original planning of the measurements, if you miss parts of the FORC space, or if your measurements do not have enough resolution, there is nothing which can be done.
There's 2 online comments I was hoping to try and get to. Can I borrow the microphone for just a minute? Or you can read, if you wanted to read them off, that's fine too. Yeah, there you go. Yeah. We have one online comment from Aldo Winkler, where he's writing, since you talked about the time dependence of FORCs, what about the influence of the averaging time? That it is often a neglected factor. It's too large and it's the particles and SD threshold. If it's 100 milliseconds or less, FORCs can be very noisy and at risk to miss other components too. Do you suggest performing FORCs at different averaging times?
Okay, now I just got off somehow. But anyways, maybe while you're fixing that. If I understand correctly, to try different averaging time. Okay. If you have a very weak sample, basically increasing the average time in theory is beneficial, but in practice is not beneficial. For 2 reasons. One is the temperature problems that we are seeing. So the longer individual curves takes, the more chances there are that you are getting problems. And the second one, that even the regular noise is correlated in time. Because, for instance, part of the noise is turbulence of the air. And this is correlated noise. So you don't get anything more if you have your averaging time going beyond 0.2 seconds, in my opinion. If you have noise problem, so your sample is very weak, my recommendation is stack measurements. So repeat your measurement by keeping the averaging time small. And stacking is something that I think LIFO for sure, probably FORCnet as well, can deal with. So you can import all your FORC measurements in a stack and average them.
And there's an online question from Win. Win should unmute and go for it.
Yeah, sorry. Hi, Ron. That was a great talk. There were 2 questions I had, and it's mostly on interpretation, as you might expect, so I don't want to take too much time up on this session, but if you have a second. I think it's on slide 32, you showed some very nice FORC diagrams of, 35, I'm sorry, is it on, it was labeled 32 and I took a note of it.
Yeah.
Yeah, I think that's the one of you now, so yeah.
I don't know how to, even if I click share, it doesn't work.
Oh, it doesn't, you don't need to show it in full. I was just wondering, will those experimentally measured, or, because again, you have a very clear vortex signature, where I don't seem to be able to reproduce. I just wondered if it would.
So the $1 million question. So the left FORC diagram is one of the calculations that were done for multi-stranded magnetosome chains in the paper on Amor and others in 2022. So these are simulations. If you wonder about the quality, it's simply because I simulated 1 million of chains with different configurations. The other 2 diagrams are real. They are measurements. The clusters are particular types of genetically modified bacteria, which instead of synthesizing chains, they synthesize clusters, but of few particles, not huge cluster as those that you would get if you extract the magnetosomes, but really small cluster made of 10 or 12 or 15 particles. And the FORC diagram on the right-hand side is one of the classical Dumas, I think, Dumas paper iron loss.
Okay, yeah. So those intrinsically have a very high anisotropy, I guess.
About the iron dots, I don't know, because they are actually, well, the planner on isotropy in that case, right, because they were this.
Okay, I think we're now reached a point where we need to pause on the conversation, because it's lunchtime. So we're gonna take a pause for a little bit. We're all gonna head over to Tate Hall, which is where the building that the IRM actually resides in. This is a short 5-minute walk in that general direction. Any of us from the IRM can help lead you over there if you like. Lunch will be in the atrium area of the building. We're gonna resume in about an hour, so it's not a terribly long lunch. But our hope is that we can all talk and sort of enjoy a little bit of food together there. So we'll see everybody here in about an hour, starting at 1 o'clock. Thank you.
Hi, everyone. Before you go, there will be a dinner at a place called the Caspian Bistro on Wednesday evening. Many of you, thank you for filling